Thank you all for coming and joining this late. I know that we've been giving you a lot of material for thought today, and I'd like to give you some more. I hope everybody grabbed their coffee. Yeah, sweets, excellent. Please turn off your phones, just as a courtesy for me. I'm Itamar Haber. I'm working at Redis Labs as chief of doing nothing, actually. I do all sorts of things, basically around Redis. Everything I do is around Redis. And one of the things I've done is I wrote a module. I don't know if anyone told you that Redis supports modules. Did you hear about that? So I wrote a module, and I was all like prepped to talk about it. But then a happy coincidence happened. My friend and colleague, Dvir Volk, also wrote a module and was also giving a talk here, but then his wife gave birth to a lovely baby girl, Mika, just the other week, so he cannot attend this conference this year. I'll be taking his place and be telling you about his work. And at the end, at the very end, if I'll make it, I'll also tell you a few things about my module. But my module, ReJSON, is so much more boring than what I'm going to show you now that I think it's well worth the sacrifice, personally. So, Dvir Volk and in lieu of Itamar Haber are going to show you something that Redis Labs have done. Redis Labs, the open source home of Redis, open source, and the provider of multiple Redis focused and centered solutions. I have a full slide about that, and you probably saw this slide, these two slides, so I'm not going to actually read off the screen. I'll just let you gaze at them, and here we go. So, searching in Redis, and this is basically what I'm going to talk and spend the time, at least 40 minutes out of the 42 that I have. What's searching, and what's searching in Redis? We all know that you can store stuff in Redis. We have all these wonderful, comfortable, abstract, lovely data structures that you can just shove things into them and then get them out using all sorts of commands. And if you want to store a user's profile, for example, you can store it, let's say, as a string. You get it back as getUser1. You can also use a hash if you want to start like chunking things and keeping fields. Everything is fine and dandy, but anyone coming from the non-Redis world, whether you've been burned by SQL stuff, or even if you just have in your possession some common sense, the first thing you want to do after you start putting data into Redis, you want to read it. And you come to the realization that while you can read data very easily, you actually need to know where it is. You can't search for data or actually ask Redis questions, where is the data that looks like that? I want to find it. And this is not a secret, it's a well-known fact. Even Salvatore himself, I can find a tweet where he says, Redis is not a search engine, it doesn't have indexes. It is what it is. Sorry about the next cough. So just to set the stage and put things in context, when we talk about searching, we talk about a single very important concept. It's called the index. The index is a data structure that basically allows us to search for things efficiently. What is indexing or searching? What does RediSearch do essentially? It does these three things. It eats documents. Documents are just collections of properties, values, data. So it munches on documents. It parses them. It breaks them apart to each document's constituent terms and attributes and values. It maps these terms and properties according, every term property gets mapped to its relevant document ID using something called a posting list or an inverted index. So this is the index, the index, And then searching basically becomes a very simple task. All you need to do is look at the index that you already have and match the search terms to the terms that you have in it and return to results, and that's it. Wow, it took me much less time. I guess I can talk about ReJSON. Any questions up until now? I'm just kidding. You can look more lively, but don't bother. Oh, sure. So after we covered what searching is, this is basically repeating what I said earlier. It's just a more graphic diagram to show you that a document is made out of terms. So we've got a bunch of documents, doc 1, 2, maybe 3, 2. Each document is made out of properties. For convenience, this looks like JSON at the moment, but it could be any document, any form you could conceive of. And creating the index is basically taking these properties and mapping them internally. Very, very simple stuff. So, how do we search in Redis? We talked about the index. Can we create an index using Redis? Redis, may I remind you, has several interesting data structures in it. I'm sure we can look into them and find at least 1, 2, 3, or 4 out of the 9 or so that we have now that can be usable and capable of indexing. And the answer is yes, you can do that. If you go online and search, how do I index with Redis? If you go to the web page called, I think, https:/redis.io/topics/indexes, you'll find a huge page with a lot of tips, recipes, how to index stuff using Redis. And that's an example. So if you're new to Redis, Redis has a data structure called set. It's basically a group of unique items. We can add to it members, remove from it members, and check for member existence, and do all sorts of interesting operations like intersect and difference and so forth. We can certainly use sets, and a lot of people do that, to model indexes and relationships and stuff like that. So if I'm trying to index a document, perhaps it's made up of its document IDs, doc1, and it has 2 terms, 2 words in it, hello and world. I can create 2 sets, one set for the word hello, and put into it all the occurrences, all the document IDs where that word appears. And I can create yet another set for the word world and do the same. And then I can use, for example, the sinter. Sorry, my voice is constantly. All right, and then I can use sinter to find what's that? It's basically the union, where all the document, an end operation, where all the which documents are the documents that have hello and world in them. And this is a very powerful approach. People use it, and you can take it very, very far. You can even step it up a notch and turn the volume knob all the way to 11, and use a sorted set, and then you can actually rank documents results. So I can say, for example, document number 1 for word hello is a perfect fit, whereas in document number 2, that term is only half as important and perhaps do more interesting stuff. So this is what I'd recommend you to do if you come to me at Stack Overflow with the question, how do you index data? And this is what I would have answered up until modules. But the vanilla style only takes you so far. There are a lot of limitations, a lot of obstacles. Of course, general abstract data structures are great. They allow us as developers to basically have total freedom. We don't care about the implementation. We just consume the awesomeness that is the data structure. But when you come to indexing stuff, you realize that you need to be pretty damn efficient. You need to really care about how much memory you're not wasting, but taking on top of the data that you're indexing. And especially a full text search engine where there are a lot of entries in the index, you need to keep that as tight as possible. And when you consider the fact that a sorted set, well, it's an amazing data structure, is not that optimal because every element in it consumes 60 bytes of an overhead. And when you take into account the fact that index entries are usually 1 byte, 2 bytes long, it's a huge overhead. So in that sense, a sorted set doesn't really cut it if you want to build a scalable search solution. And then there are other obstacles and challenges, like the fact that you can't really do stuff like exact search, phrase searching using a sorted set. And it just gets more and more complex. And this is basically a pain that many users feel and ask, how do we solve that? How do we search with Redis? And then life changed. It was actually a year ago, exactly a year ago. Well, probably a little bit more, not at the same stage, but on a different stage. But Salvatore stood and said, listen, guys, we're going to have modules. And we were like, oh, wow, modules. And we knew about it internally. And Veer actually was one of the proponents of the modules. He helped Salvatore bake it, test it, developing the modules that he was developing and testing the API through all that time. And modules allow us to do wonderful things. And this is not really a lecture about how to use modules or how to develop from modules. This is what we did last year. So this year we'll present you what you can do with modules that are essentially just dynamic libraries that you can load to the server while it's running at runtime and extend its abilities and capabilities with natively compiled code, adding new features, new commands, new data structures. So now everything's possible with modules, and search with modules is also possible because we can implement our own stuff. We can bring whatever we want into Redis now and use it. If we need a data structure that's more optimal, more convenient for our needs, we can do that. And we can use less memory. We control what we do. We control the amount of CPU that we use inside the module, and so forth and so forth. This is what led to RediSearch. So the one question that needs to be asked before we dive into what is RediSearch and how does it work and what does it offer is, why do it at all? Why write it from scratch? After all, if search is something that's commonly used, and I think we can all agree that search is one of the core capabilities in every application. Every service nowadays offers a search box for something. Like you go to Google, what do you see first thing? A search box. You go to Amazon, same thing. You see there a search box. You search for items, but it's search capability. Facebook, Twitter, same thing. I was surprised to find search boxes everywhere because, and you overlook them. It's trivial. We require search. And of course, if this is such a necessity, there are existing solutions out there for search. People have implemented search engines before, so why write it from scratch? And Veer's reply, by the way, he worked on this presentation, so I'm just his proxy. Every joke in them is his. I'm trying to mimic him poorly. But I do share his opinion. Most of these search engines are written in Java, no offense to any Java people here, but they are written in Java with everything and anything that is implied by that. They're usually very complex, bloated, big things. You can't make a sense of where they begin and start, you know, the kind of beasts I'm talking about. And perhaps most importantly, without all our, or my conceptions and misconceptions, these technologies were primarily written for spinning metal disks in mind, just like relational databases of old. And we're no longer in that age. We're talking about different things nowadays. Not for everything. It's not it's not a silver hammer, golden hammer, a silver bullet or something, but there are use cases where you're looking for search in real time. And existing technologies just don't cut it. Plus, where's the fun in that? Veer had a lot of time on his hands and wanted to do the impossible. This is RediSearch. So it's a completely from scratch written in C search engine. Not, well, some of it is not from scratch because modules do allow us to import existing libraries into Redis. So some of the logic it's unnecessarily needs to be rewritten. Even RediSearch has some embedded parts like the Itamar engine that just imports from another project. It has its own arsenal of optimized data structure. Again, this is very important just to keep in mind because optimized means we're using Redis and the server's resources to the best of our abilities. And it goes all through the module. I won't take you through all the optimizations that Vera's put in, but believe me, there are plenty of that. He saves every half bit he can. It's amazing what he does there. At its core, what it does is store documents as Redis hashes. So actually, we do use the core Redis data structure hash to store a document, a collection of properties, but this is optional. You don't have to store a document inside Redis as a hash. You can actually store the document in MySQL, Mongo, S3, your hard drive, you name it, but just keep the index in Redis. So this is like a tunable option and offers extremely fast indexing and search. Extremely fast, like nothing you've seen before in searches. Extremely fast, meaning Redis fast. Offers basically every search capability that you can think of, whether it's text properties, numeric properties, and even geospatial properties that we also use the Redis geosets to implement with. Non-blocking updates and delete basically means you can start working with the index, updating it and querying it at the same time. I'll show it to you in a second. And the nicest thing is that it was built from day one to be scalable. It's not just a solution that runs neatly inside a single Redis instance serving up to this much amount of data. You can scale it across a cluster. Very impressive stuff. So let's see a demo. Here it is. Ready? The demo consists of creating an index, adding items to an index, and then searching the index. If you'll look carefully, you'll see that the entire demo fits into a single slide, so it can't be that complex, right? And it isn't. The first line that's up there should look very familiar. It actually uses even similar syntax to SQL. We create an index. Every command that the RediSearch module exposes begins with the prefix FT, which stands for full text, then a period, and then the command's name. The command's name is create, so we create something, it's an index, we give it a name, and then we give it a bunch of fields that describe the index's schema. Once that's done, we can basically run ahead and start adding documents. We can actually query the index, but it's empty, so let's add a couple of documents. We do that with the ft add command. And we're adding documents, we're giving them a document ID, then we're giving them each a score. It's a user-provided score, so this document scores this, this, and that. If you don't care about that, give all the documents the same score, but you can give different documents different scores if you want them to be ranked higher when you search for specific terms. And then you just start feeding fields with their respective values. So text, some sort of text, maybe the description of the product, price, some sort of a numerical property, probably the price of that product, and we can keep on doing that until we're ready to perform a search. And the search is done with the ft search command that gets an index name and a query and returns the results. Nothing really groundbreaking here in the sense that you really won't expect anything less. The beauty of it is that it's there and it's working. So it's not just a slide, it's an actual demo. Well, not what I show you, but it's an actual product used in production nowadays by at least 3 customers that I know of. I said that RediSearch brings into the room a few of its own data structures. These are the data structures that it adds. None of them is really accessible like Redis's data structures. That is, you can't work with them directly. You just work with them with the API of create, index, add, and search. But internally, what it does, it maintains all these things. I won't go into too much details because I'm running short in time, but do feel free to dive into the code, read the documentation, catch me here online or wherever. There is also very accessible online emails, GitHub repository. We're craving for feedback. Your input is important, and we're happy to take your questions. A few words about what it means after we've built the index, and let's suppose that all these beautiful data structures are in place. We've got an inverted index, and we've got a document mapping table. All the good stuff is in place, but what does actually searching means? The user submits a query, but what do we do with that? What happens to a query once it's submitted to RediSearch? So first, you need to appreciate the beauty and the colorfulness of the search commands syntax. It's pretty impressive. Looks like anything you'd find in an Oracle manual, perhaps. It's pretty intimidating, but once you get over the puke, just read the docs. They're very straightforward. Every option has a very simple explanation. And everything really falls into place once you read the manual. But once you search Redis, once you give it a search, RediSearch, once you send a query to RediSearch, this is what basically happens. The query comes in and someone, RediSearch, but something in RediSearch needs to parse the query first, make sure that it's syntactically correct and understand what parts it is made of. There's a small but very significant part that goes on after we parse the query, which is called query expansion. That means taking terms in the original query and expanding them according to your rules or the rules of the index. So expanding could be like replacing a term in the query with its stem, stemming words. You can take the stem and search for the stem instead of the exact word. So this is a query expansion mechanism. Once the query has been parsed and expanded, it moves into the execution phase where the engine runs basically on the index and tries to execute your query. As this goes along, each document that matches the query's parameters gets ranked. If a document fits the search parameters, it gets ranked and scored. And then we keep a top-end sort of structure where the top ranking documents for the result are stored. Once this is done, and optionally we can return to you the entire document. This is if the document is stored in RediSearch, and if you're asking for the document's body, we can load the document itself after we've scored it and found it. And then, of course, remains returning the response. So at a very high level, this is how a query happens. And if you dive into what happens during query execution, so here are a few interesting parts. You can see that you can't see, but we're telling you that RediSearch operates, takes the approach of a document at a time. This is in contrast to the other approach that you can use, which is term at a time. When you're in document at a time, it means that you're taking each document and matching all the terms against it. When you're doing term at a time, you're taking one term and trying to match all the documents against it, and so forth. So we're using the first approach. We go over the index document by document and try to match the terms to it. The nice thing that Weir wanted me to highlight is that the indexes, traversing the index, is basically implemented as an iterator. And if you don't know what that is, you're lucky. Be blessed. You don't really need to understand what that means. But if it's already too late for you and you understand what iterators are, then I can tell you that it's basically a very convenient way to save on memory. Each time we traverse the index, we just keep a little bit of information. We don't keep a chunk and then try to traverse it. It's very efficient. At every iteration on the index, we just keep the minimal amount of state data. And as this goes along, as we collect information, we score each document using a ranking function, and the top end results are, as we work the index, copied upwards on a heap. that is pre-allocated the number of results that we want. So at any given time, we have the top results that we need. We don't need to keep all the matching in documents, then sort them by rank, and then just trim the top and return it to you. We actually keep the top at any given time. The reason I'm going into this is to show you that there's a lot of thought. We're trying to make this not only optimal in the sense that it runs fast, but in the sense that it doesn't take too much resources, that it takes only the minimal amount. I did mention the fact, I won't dive into this slide, but I did mention the fact that each and every document gets ranked. So the component that ranks documents is called the scoring function. Each document is scored. Top-end documents get collected. Various acronyms and professional terms to show that we understand what we're doing. But the nice thing is, and perhaps the most impressive one, is the fact that you can actually write your own scoring function. So this is the scoring function that we use, the default. We use a mix of common best practices, an algorithm called term frequency inverse document, whatever, and proximity boosts and stuff like that, but it doesn't mean that you have to play by our rules. In fact, one of our customers in production implemented her, actually all of them did that by now, her own function according to the documents and what he wants to find. So that's perfectly doable. Any questions up until now? Because the next part is, oh, yes?
Can you just talk a bit about how the numeric indexes work, how the numbers are reflected?
Oh yeah, definitely, sure. I'll repeat the question. The question was, how are numeric indexes ordered or implemented? How do they work? There's a very, very brief reference here. It's called a range tree. It's a data structure, a very cool data structure that basically, one of the cool things about it is that its name basically describes everything you need to know about it. It's a tree-like structure where it keeps ranges. And that's like the top-like idea. What Veer did, and I remember I was sitting in the same room and he was like pulling, well, he's pretty bald like me, but he was pulling this data structure out of his head because what he did there is not just a trivial range tree, which you can look up in Wikipedia and like, okay, I can implement that, sure. He made something beautiful there. It's a tree that's made of linked blocks. So it pre-allocates stuff so we don't pay a lot of price when you're adding and updating the index. But at the same time, it gives you a very good balance between the tree's height and beautiful stuff. I could like spend an hour just talking about what we did there. But basically if you look at a range tree, you understand that in terms of documents, every property, numerical property is just a term. So the range becomes a set of terms. You don't need to actually do real ranges. You just need to do it for the terms that you have.
Just a follow-up. So if you're doing a very large range query, let's say from the minimum to the max value,
Yeah.
does that imply it's going to basically have to scan many times each of these nodes of the tree?
It would if it could have been that way, but Veer is also keeping all sorts of, again, I wish he was here. He would have like sat down with you and show you how he did it. He's very proud of the code, and he should be. But it's simpler than what I'm trying to show now due to the briefness of time. Yeah. Proximity boosting is just a scoring aid. So if you're searching for terms and you're saying hello world, proximity boosting means the documents where hello world, the two words, the two terms, appear in closer proximity will be ranked higher. That's the entire thing. So if you have hello blah 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 blah, blah world, as opposed to hello world will be 1 and hello blah blah world will be 099 or something. Yes, Dimitri. Maybe I don't remember. I'll get back to you. Sorry? Yeah, that's right. Slop, I think, means that, but I wasn't sure. I'll check and I'll return. Yes?
Do you guys support GeoHash?
We don't support geohash. We use geohash internally to do geo filtering. So you can put the set of coordinates and tell the indexer index that, and then do a query on the range of coordinates. Internally, it's encoded as a geohash, but that's an implementation detail.
How do you have to convert a geohash to geo coordinates to satisfy the index?
Yeah, right now. But if you want, we can add just geohash field types if that's a requirement. That's the beauty of it, by the way. We're very receptive. All right, I'm going to run through RediSearch's query language. I'm sorry, I'll come back to you. I promise. If we'll have time, and if not, I'll corner you in the corridor. So the query language is pretty self-explanatory. I'm going to run through it. It's just like using Google. So if you want to search for, let's say, hello world, so you just type in hello world. You can also add a pair of parentheses just to make sure that you're comfortable with it, but it's nothing more than a visual aid to group them. The terms, between the terms, you see an implicit end. If you want to do an exact phrase match, you just use the quotes around the sentence and you'll get an exact phrase match. You can also use the union operator and search for something or something else using the pipe character. Then comes the really neat part, because if you remember, an index is made of a set of fields. So while earlier I was doing a generic search and my hello world could have been anywhere in the document, in the title, body, price, whatever, now I'm limiting my search actually to a specific field called title. Very cool stuff. I can actually say I want to search in this or that field, just like I did earlier with the OR operator, but here I'm selecting multiple fields. Multiple field selectors, again, can be used in the same query, like you're seeing here. Then comes another nice part. You've got your numeric ranges. Numeric ranges in RediSearch behave or use the same terminologies and conventions that ranges in Redis have, so you can search for well, implicitly, when you're searching, your ranges are inclusive, although you can use the bracket or the parenthesis sign, sorry, to indicate an exclusive range, and of course, -inf and +inf to indicate ad infinity. Then there's the optional, it's that little tilde sign there, the optional clause, which basically says, well, I'll be cool if that appears, but don't fret about it, and basically all it does is just boosts the document score at the final ranking. And of course, you can't have a real search engine without some negativity in it, so you can also drop things and specify that you don't want certain words in your results. You can do prefix searches, so anything that starts with hello world will come back, and of course your queries are by no means limited to a single term. You can combine the terms and create as powerful queries as you would like. Perhaps a demo would be nice. So here's a very short demo that basically shows you what we're talking about. And the demo is a demo in the sense that I'm demoing it, but it's real. It's not a PDF, it's out there. First thing that I'm going to show you is a screen taken out of our administration user interface of the Redis Enterprise cluster. So the guys back home set up a cluster, not a too big one, I guess. It's got only 8 nodes. Each of them has about 60 gigs of RAM, so overall we have probably 300 gigabytes, a little more basically, to work with. And with our solution, each one of these servers actually runs multiple shards, in this case 10. So there are 10 Redis processes running on each one of the nodes. So this is the topology of the database. We can go to the database view and, oh, here we are. So this is search demo. Very good. Search demo is currently very idle. You can see that it's doing nothing, and I'm not going to demo you the UI. What I'm demoing you is this beautiful little application, also courtesy of Dvir, that basically, I'll click here. What I'm doing now, this application is adding documents to the index. Specifically, we're adding Reddit discussions. So the index is just growing with more and more Reddit discussions. You can see the speed that this is happening. All right, so we're touching about 70K documents, indexed documents, that is, ladies and gentlemen, per second. All right, and each document, I don't remember its size, but it's like this big, or it's a comment, so a few hundred bytes. And everything happens at sub-millisecond latency, so every addition to the index. Of course, nothing else is happening in the system. Here I have my search box, which I can actually, oh, wait a minute. Okay, so here I have my search box, which I can actually use. I can search for Redis. I can search for Redis and then say, I think, author. All right, cool. 38 results. I can do the same. Nice. And then I can also actually, so that's one query. I'm just showing you that I can query the index as it's running. But let's click this button. This button does a very funny thing. It takes my query and starts benchmarking Redis with it. So this query is not that hard. It's not that difficult, I think. You could see that the documents per second speed had dropped because I'm actually running a lot of queries here. And but latency is stayed by the same. And then you can see my search stats. So this query pushes about 10K operations per second. Let's try and let's do something else. Let's just look for Redis, perhaps. It will be slightly faster. Yeah, a bit more. So you're seeing here about 10K operations per second of search plus about 35K operations of indexes being added in real time. And no current search engine can provide that to you. Like, yeah. It is. Once I turn off the benchmark, you can see the gouge jumping right back, giving us back that nice performance, close to 70K. Of course, we can change and play with the topology, different settings. Let me pause the thing for a sec. Different settings will yield different results. It all, you know, there's no one generic configuration, but this is the demo. I did mention that RediSearch is extendable. It has its own internal sub-module system. You can basically write modules for RediSearch, which is sort of an inception-like thing going on here, because RediSearch is a model by itself, so it supports its own custom ranking functions, and Dvir is adding a lot of customization to the product, so everyone can pick it up and actually use it in their own use case optimally. Just one brief slide about a very important thing that RediSearch also offhandedly offers. I don't have time to go into the entire thing, but basically autocomplete, you're probably familiar with that sort of functionality where you start typing and we complete it for you. So as a bonus, RediSearch also has that capability. You can play with it. Just one slide. Go. Scaling RediSearch, very important. We did see RediSearch in action, right? But, and I showed you the cluster size, how all that happens. So we do need a way to scale RediSearch. We don't really think that a single index can be hosted by a single server. Of course, this is much more complex than just designing a single server system. What we've done with Dvir and our R&D back home, we basically built a coordinator element and partitioned the index across many nodes. This is how it looks like in very gross terms. We've got our Redis. On top of it, we've got the RediSearch engine. And on top of that, we've got a coordinator. And bam, we've got the RediSearch shard. And then we can build these shards. We can stack them in different servers. We can actually use this model to throw queries into the cluster. So if I'm searching for something and I'm, as a Redis client, connected to just one node, one shard in one node, this shard will basically go out and use what's called a fully connected fan out and in pattern. It will go out, fetch all the results, collect them for me from all the different shards, all the partitions of the index, and return them to me. This is very efficient up to a certain cluster size. Once you cross that threshold, it could become a pain because interconnectedness of all things has a price. So we do support another mode that we switch to once we grow. And this is basically a tree-based fan-out model where the node that we connect to knows how to connect to other nodes, and then locally on each node we collect the results. The results are collected locally on the node level and then get returned to the coordinate node. This is a very old slide. The numbers are much, much better, but we need a performance slide to close the thing. Thank you very much. Don't clap your hands yet. Thank you, thank you. No, clap them, I like that. I'm running forward here. Sorry. Yeah, that's one. So, 3.5 minutes to do that. Easy peasy. This is why I came here, by the way. This is my claim to fame, right? Tomorrow you can see me filling in for someone else. I'm just kidding. I love my job. I do all sorts of things. ReJSON. It's actually a very boring subject. I don't need more than 3 minutes for it. So I don't know if you've heard about JSON, but this is JSON. This is the definition. Highly compressible. That's the entire spec. We could talk about it. It fits into one slide, but that's not the point. We're not here to talk about JSON. What I found is that JSON, despite the spec, is filled with holes and misunderstandings and fallacies. And if you were looking, and finally I found someone who actually went and wrote the entire thing, summarizing each one of the panes. I was like reading, yeah, that's right. Parsing JSON is a minefield. There's a spec and it's riddled with holes. But we don't care about that because other people already implemented JSON for us. And JSON is a standard. And fact number one, it's used by everyone. You can't escape it. Fact number two, there are many of these users who use JSON that are also using Redis. If we try to analyze this and we think there's some sort of intersect between the ones who use JSON and the ones who use Redis, on the other hand, from us, not from them, we find that there are two ways or two orthodox ways to store JSON in Redis. The first is take your JSON, it's just a string value. Redis can certainly support string values, just store it serialized as is, get it serialized and deserialize it in the client, and everything's peachy. If you throw in some Lua scripting, and I like Lua, you can go pretty far with that approach. Very powerful stuff. The other way to do it, JSON, is you take the JSON, you explode it, and just store it in a hash, and that's also a great way to work with JSON. This is what we've done before modules were available. Both approaches have cons and pros. If I had 2 more minutes, I would probably bore you with them. We don't, so I'll skip that. ReJSON, a playful play of words on the topic of Redis and JSON. I hope you can find the irony in that. Well, I was looking for another name, and this is the default, right? And nobody suggested anything, so we stuck with that. Basically, it means JSON in Redis. And what it is, it's just yet another module. It does what you expect. It brings a JSON data type into Redis, a way to take a JSON document, store it as JSON in Redis. So you pick JSON, you throw it down Redis's throat. Redis understands what to tell them, and we store it internally in a tree-like data structure, so, which makes sense because a JSON document is basically a tree, so we use a tree structure. We can add all kinds of nice capabilities, like we can make sure that if you're talking numbers, you'll keep on talking numbers, give you nice atomic operations like Redis does on numbers, strings, whatever. And here's this brief demo of ReJSON, just setting a simple document, doing a get, doing a set, or basically doing a set, and then a get, one of a scalar, the other of an object. You can access the path inside a document if you want. A graph, because we need that too. So this is sort of what happens behind the scenes. We do need a performance benchmark. Yet again, this performance benchmark is very old. I should redo it. But what basically tries to show is a comparison between how ReJSON acts and the standard orthodox ways of doing Redis and JSON. And unsurprisingly, does well where we expect it to do well. This is the entire corpus of commands. If you have more, I'll be happy to add them if you've got other ideas. ReJSON, just like RediSearch, has its own website. I didn't linger on it earlier, but it's online. Both RediSearch and ReJSON are open source, very well documented. We think we'd be happy to get your pull requests, feature requests, and so forth, questions, and so forth. Catch me. Thank you very much. I'm out of time.